Hello students, in this video we'll discuss orthogonality in Rn and some immediate consequences of orthogonality. So we say that two vectors, that x and y in Rn are orthogonal to each other if x dot y is equal to 0, right? Orthogonal is just another way of saying they're perpendicular to each other. Okay? This is just a generalization of the idea of being perpendicular. Okay? All right. And of course, this stems from multivariable calculus, in which case we know from Calc 3, we know the following. We know that in Calc 3, there's a way of defining that x dot y over the length of x, the length of y, is the cosine of the angle between them, right? And of course, x dot y equals 0 forces theta to be pi over 2, and that means they're perpendicular to each other. So this is a Calc 3 fact that we're going to use, that we're going to generalize to say that they're orthogonal if their dot product is equal to 0, right? And in a genuine way, that describes a geometric construction of these things, okay? Excellent. All right, so what are some consequences of this, right? So one immediate consequence of this is the Pythagorean Theorem in Rn. Again, we're talking about the Pythagorean Theorem in high-dimensional space. The ordinary Pythagorean Theorem is very simple to prove, right, in classical Euclidean geometry, but we want to prove it in Rn using this notion of orthogonality, right? So what does this say? This says that if U is orthogonal to V, then the length of U plus V quantity squared, that's the side length of the triangle, is going to be the length of U squared plus the length of V squared. And of course, the proof of this is straightforward. The proof of all these facts stems from the orthogonality, right? So proof of this fact is really easy. It's just the length of U plus V quantity squared is just U plus V dot U plus V, right? And now we can FOIL this out. This is U dot U plus, by symmetry, 2U dot V plus V dot V, right? And now since U and V are orthogonal to each other, perpendicular, that term is gone, and we get exactly what we want, just the length of U squared plus the length of V squared. Okay, excellent. So that's the Pythagorean Theorem. And of course, we can do this by induction, right? So by induction, if U1 through UN are mutually perpendicular, mutually orthogonal, meaning that if you do the dot product of any two of them, you get 0, then we can show that the length of U1 plus all the way down to UN quantity squared, by opening up all the brackets in the inner product, is going to be the sum of the squares of the lengths of the U's, right? Squares. Great. So that's an immediate consequence just by passing it through by induction, right? The second consequence I want to talk about is this this orthogonal decomposition, right? So this is orthogonal decomposition.
Mountains on this.
All right, and so what I want to do now is I want to say, let's take a vector over here, V, in my space, abstractly visualized like this, and the vector over here, U. And what I want to do is I want to break U into V into two parts. So I want to say that V is going to be broken into a part. I'm going to call that part V parallel plus V perpendicular, where V parallel is in the direction of U, right? So V parallel is lambda times this vector over here, U, and V perpendicular dot V parallel is equal to 0, right? So I want those two conditions for my orthogonal decomposition to be true. So what will these conditions tell me over here? These conditions over here, so if I want to find out what this lambda is, I can write this over here in the following way. I can write this as V is equal to lambda U plus V perpendicular, right? And I'm going to dot both sides with U, right? So that says that V dot U is going to be lambda U dot U plus v perp dot u. But by assumption, v perp dot u is equal to 0, right? Because they're perpendicular. By the assumption, that's equal to 0. So this is just lambda, the length of u, quantity squared. So what does that tell us? That tells us that this lambda, so what does that tell us? That tells us that lambda, therefore, is u dot v by symmetry over the length of u squared. And this gives us our orthogonal decomposition, right? So what this tells me is exactly that my v is equal to u dot v over the length of u squared in the direction of u. And then what? And then we'll have what? We'll have plus v minus this expression, v minus u dot v over the length of u squared u. So that gives me a decomposition of v into something in the direction of u. And so what this is over here, as we're going to see in later videos, we're going to call this thing over here the orthogonal projection onto the space spanned by u. So this is the projection onto the vector u of v. It's a projection operator, and this is the projection operator onto the complement, onto, I'm going to call that, just for simplicity, u perp of the vector v, right? So in other words, I'm decomposing v into the sum of projections onto different subspaces. The first projection is onto the subspace that's generated by v, and the second projection is the projection of the subspace generated by everything that's perpendicular to v. And that plays an important role, that other subspace, that perpendicular subspace, plays an important role in understanding the structure of the space in terms of orthogonal complements and null spaces of perpendicular complements and things of this sort. Thank you very much.